Greetings, I'm Elias Kazmeridis from the Department of Computer Science and Engineering of University of Ioannina, and I'm going to present you our work with Vasilis Dimakopoulos named OpenMP Offloading in the Jetson Nano platform. The presentation begins with an introduction to the background of this work. Then we will talk about OpenMP and how its device model enables heterogeneous programming. In the third section, we present our extensions to the translator part of the OpenCompiler in order to support GPUs. And in the fourth section, we present the runtime extensions to the compiler. Finally, we provide some experimental results, as well as a summary of our work, and close this presentation with our plans for future work. So let's begin with the introduction. It's a fact that modern computing systems are heterogeneous. That means that a single computer can contain different subsystems, all of which can cooperate for accelerating specific workloads. For example, GPUs accelerate graphic workloads, DSPs can be used for audio signal processing, etc. Embedded systems have also become heterogeneous because the applications require more performance. Examples of heterogeneous embedded systems is the paralleler board by Adaptiva and of course the Jetson Nano platform. However, it is difficult to program such systems because the programmer basically needs to use different lower level APIs to exploit their hardware. As a result, the complexity of the process increases and the portability of the applications drops. Let's take Jetson Nano for example. It's a small but power-efficient CUDA platform with a quad-core ARM CPU and a 128-core NVIDIA GPU. Currently, different APIs are available depending on the computation the programmer wants to perform. But which is the basic way to program a Jetson Nano? Well, CUDA is the official programming model for developing applications for Jetson Nano. And in this scenario, first NVCC translates CUDA code to a host file and a device file. The host file loads and executes the kernel through CUDA API calls. The device file contains the kernel code which will be executed. But what about higher level programming models? We can use them to replace multiple low level APIs. Well, a popular example is OpenMP, which is proposed in many works. It's also popular and promising. In fact, its version 4 introduced the device model, which enabled heterogeneous programming. However, despite the variety of supported APIs, support for Jetson Nano is still not available. Let's take a look to the current compiler support. The standard compilers included in the Jetpack SDK, that is NVCC and GCC, currently supported only CPU offloading. We managed to build the latest versions of GCC and they succeeded, but GPU offloading was impossible. CLang could not pass the build process in the 2 GB version of the board, and NVC and VC++ supported some OpenMP functionality, but it was only available for CUDA architecture version greater than or equal to 7.0. Our work introduces the first full OpenMP implementation for the Jetson Nano platform, offering complete offloading capabilities to the Maxwell GPU, support for OpenMP within the device code, and it comes as an extension of the OMP compiler. An interesting fact is that through our experimental results, we saw that our performance was comparable to pure CUDA code. Let's proceed with the OpenMP section. First of all, OpenMP version 4.0 introduced the device model, and now through this model, heterogeneous programming is possible. All installed coprocessors in a single system are visible as devices. But what is a device? It's simple. A device is a logical execution engine with its own memory, and the compiler exposes the devices to the programmer through the OpenMP API. A basic feature of the device model is offloading. The programmer accelerates specific areas of code called kernels by offloading them to an OpenMP device. The only requirement is that the device must be installed to the main system and connected to the host processor. Data needed by a kernel must be mapped as to or from, depending on whether they are used as input or output. The compiler decides which mapping method to use. For example, it can use unified memory and allow direct memory access, or it can use copying. All data that reside in device memory form the data environment of the device. This environment can be created or modified at any time by the programmer. The processes we described can be triggered by specific constructs. For example, the target directive is used specifically for offloading, and map clauses are used for mapping data to or from the data environment. Let's take a look at this example. It is a simple AX plus Y kernel. We can see that it contains a target directive with a parallel for construct in its body. How does this work? The target directive will offload the contained code region to the device. Variables A, size, as well as the X array will be mapped as to because they are input data. On the other hand, the Y array is mapped as to from because it must be firstly moved to the data environment and updated in the CPU upon exiting the target region. The parallel for construct exists within a target directive, so it will spawn a number of device threads that will execute the for loop. Now a few words about our extensions we need to make to the OpenMP compiler in order to support GPUs. First of all, what is OpenMP? OpenMP is an open source lightweight OpenMP compiler. It consists of the source-to-source translator, which basically translates an OpenMP program to a multi-threaded C program. First, the source file for host execution is generated, with its OpenMP directive being transformed to equivalent C code with function calls. And for target regions, we also need to generate kernel files per target region. The second component of OpenMP is the runtime system, which is a collection of host and device libraries. Those libraries provide implementation of functions called within a transformed OpenMP directive. Let's take a closer look to the OpenMP compilation chain. Well, first the user program is passed to the transformation and analysis phase. But what does this phase do? Well, the two most important features of this phase are the abstract syntax tree, or as we call AST, as well as outlining. The first one is used for the user program representation, and the second one is the method of extracting code regions to functions and replacing those functions with a function call. Next we have the code generation phase. This phase produces multiple source files, with one of them being the host source file and the other files being the kernel files. Those kernel files are categorized into two types, generic and GPU kernel files. In this presentation we focus on the GPU ones, which are passed to the NVSync compiler in order to be compiled into GPU binaries. So, we needed to extend the two described phases. The first extension is about multiple construct transformation. This means that instead of having a single way to transform constructs, we can now have multiple ways. This feature was necessary because GPUs require different transformations, and we also want to keep the generic way of transforming constructs. Our second contribution is the support for compiled target constructs, with the most important being target teams distribute, and target teams distribute parallel for. In our case, target teams basically generates code grid that will execute the code region. However, each block contains one thread only, the team master. Target teams distributes the iterations of the loop across the team masters, and target teams distribute parallel 4 launches multi-threaded blocks and distributes the iterations across them. Our third extension is the support for standalone parallel regions within the offloaded code. This task is non-trivial as the OpenMP fork join model does not match the SIMD nature of GPUs. However, the literature proposes many solutions, for example the if master sim, the control loop with inspector executor, and the master worker sim. We selected the third one, the master worker sim. Now some quick information about the sim. It relies on CUDA warps and it basically splits them into master and worker warps. The concept is that one thread from the master warp registers and assigns encountered parallel regions to the worker warps. Let's see a quick example of how OMP transforms an ad hoc parallel region to a master worker region. As we can see, workers are separated from the master warp using an if-else statement. We have shared memory utilization and also the registration of a parallel region. Workers operate on the worker function. These were our translator extensions, and now let's proceed to the GPU runtime system of OMP. First of all, we need to give some information about the organization of the offloading system of OMP. This system is a collection of modules. Each module implements OpenMP support for a specific device class. One module has two parts. The host part, which is an interface between the host CPU and the device, and the device part, which is for supporting OpenMP the device code. What we did was create a new module called CUDA-dev in order to target the Maxwell GPU of Jetson Nano, but of course the module is quite generic and can target other GPUs as well. The host part of CUDA-dev covers device initialization and finalization, memory allocation and transfers, as well as kernel launch. Now let's talk about the kernel launch. It consists of three phases. The first one is the loading phase, in which the kernel function is located and loaded from the kernel file. The second one is the parameter preparation phase, in which we prepare the parameters for the kernel. And the last one is the launch phase, which performs the actual kernel launch with the specified CUDA grid and block dimensions using the parameters we have previously prepared. The device part of CUDA-dev contains the implementation of OpenMP functionality within the offloaded kernels. The most important operations of the device part are the following. First of all, the parallel regions. We support both combined and non-combined parallel regions. Work sharing, which consists of loop schedules, static, dynamic, and guided. The sections directive as well as the single directive. And finally, synchronization, which is locks and critical regions as well as barriers. After all this information, let's proceed to the experimental results. What we did was compare existing CUDA applications to their OpenMP equivalents in order to test our performance. Specifically, the CUDA applications were obtained from the Polybench ACK suite, and the OpenMP applications were obtained from the Unibench suite. Unibench is a remake of a Polybench ACK, and basically the benchmarks use OpenMP target constructs instead of CUDA code for offloading. As far as the evaluation of our work is concerned, we used the Jetson Nano 2GB board. It has CUDA 5.3 and Jetpack version 4.6, which has the CUDA toolkit 10.2. It uses NVCC and GCC as standard compilers, and OMP basically bases its compilation chain on the standard toolkit because it's lightweight. We report the results for 6 applications obtained from the linear algebra and stencil categories of Unibench suite. We have 1 stencil application, 4 kernel applications, and 1 solver application. All experiments are based on matrix operations. We have double nested for loops in all applications except for 3D-conf that uses triple nested for loops because it performs 3D convolution, and the problem size is parameterizable. This is our configuration, the problem sizes for each application as well as the block dimensions used for the kernels. Now let's begin with the first 2 applications. We see that for 3D-conf we are almost identical to the CUDA equivalent. For big G we can see that there is a small difference in the 1024 problem size. And for the last problem sizes we see that this difference decreases. The next 2 applications, ATAX and MVT, we see that there are minor differences in the execution time. So we have generally good performance. And now the last 2 applications, GEM and Gram-Schmidt. In GEM we see that we are almost identical to CUDA, but in the last problem size there is a large difference in the execution time. We are trying to investigate the reason. And also for Gram-Schmidt we see that for every problem size there is a small delay in our implementation. We are also trying to figure out why does this happen. Now a summary. We present the first full-fledged OpenMP implementation on the Jetson Nano 2GB developer kit. Our implementation is based on the OpenMP compiler. First of all, the translator part of OMP was extended in order to support CUDA-C kernel sources. And secondly, the runtime was augmented with the CUDA dev module, which offers complete CUDA device handling and support for OpenMP within the offloaded kernel. Of course, it can support other GPUs as well, other CUDA GPUs as well. And in terms of performance, our implementation is very close to the pure CUDA-C code. For future work, our goal is to tune our implementation in order to support other CUDA architectures as well, because each architecture introduces new features that we must take advantage of. In order to tune our implementation, we need to work in both the translator and the runtime part of OMP. And of course, we also aim to optimize the current CUDA dev runtime system in order to achieve better performance. Thank you for letting me present our work, and of course, thank you for your attention.